Good afternoon. Today we got an exciting afternoon. We're going to talk about amides, and also I've got an important announcement to make later today. And let's get going. Everybody see my whiteboard? I had some minor difficulties earlier. I think I had just too many files open. All right. Now, just a quick review. How do you make an amide? You take a carboxylic acid and react it with an amine. And again, the general reaction, carboxylic acid plus an amine. And remember, R prime and R double prime can be hydrogen. And if both are hydrogen, we're talking about ammonia. And you form an amide. And we did some last week, but let's do one more to start out the day. And have some fun. What would be the product or products for the following? Let me remind you, amines do not react with aromatic rings directly, at least that I know of. And trust me, I know a lot about this area. I've worked in it long enough. And when you're done, give me a thumbs up. Oh, by the way, she liked the part in the video when I talked about why natural gas smells. And she also liked when I do this, 4 bonds to carbon. But I promised I'd give her idea a try, and I will. All right, if you're done, give me a thumbs up. All right, I don't know how we're gonna do it, so let's try out. Let me do this. Let's go out of share. Let me unpin myself. All right, why don't you hold up your answers, what you think you got, to your webcam, for those who got your webcam on. Let's see. Sort of hard to. All right, let's try something. Undo your mic and make some noise so you can be on the screen. Unmute your mic.
Hello.
Now hold up your paper, Tom.
Couldn't do it.
All right.
Still trying to figure.
All right. How about anybody else want to hold up their paper? Say something, Martin.
This is my answer. I don't know if you guys are able to cipher it.
To see it. Okay. Thank you. All right. Hold on one second. Do question 1. If you like how this is going, say yes. If you don't like holding it up and everything, say no. Can you see that? All right, looks like the bulk of you don't like it. We'll try it again in a little while. I'll tell you what, we'll experiment today. All right, let's do this first. Question is, what's the product or product for the following? And we look at here, remember, when you look at a molecule, what's different? Ooh, oxygens, hydrox group and a carbon double bonded to an oxygen with our group here. That's a carboxylic acid. And for those of you who still have your mic on, please mute yourself. And now what do we have here? Ooh, a nitrogen. It's got carbons and hydrogens, and that's an amine. Remember, R prime and R double prime can be hydrogen. And there should be a hydrogen on here too. And what do you get? An amide. And this will be R. I can call this methyl group R prime or R double prime. And one of these hydrogens is the other R double prime. So keep your eye on the carbonyl carbon, because that's where the fun is. And it has nitrogen. What's my R group? A benzene ring. One of the R prime is methyl, and the other is a hydrogen. Remember, except for a quaternary ammonium salt, nitrogen has 3 bonds to it. Let me remind you. Remember, nitrogen, except for a quaternary ammonium salt or amine salts, has 3, not 4 like carbon, but 3. Oops, it's broken. 3. You can tell I was never a Boy Scout. But not that there's anything wrong with being a Boy Scout. All right. I thought I'd bring you up to date. We did this last week. Oh, let's do one more synthesis. Let's have some fun with this. What 2 compounds would you react to make that molecule? And when you're done, give me a thumbs up. All right, anybody need more time? Now, in light of what the dean asked me to do, anybody want to hold up their answer? Any volunteers? Well, so much for that experiment. This part I'm going to take out of the video. Back when I started teaching organic, And even before that, general chemistry, I'd write these problems on the board. And I actually told the dean this, so I'm telling you nothing new. And I found out students would rather pull their teeth out with pliers than go to the board. And you're showing me nothing that hasn't changed. So much for the experiment. I'll tell her the truth. Most of you don't like this. But if anybody ever wants to show their answer, always feel free to ask me, can I show my answer? And the answer will be always yes. But let's do this. All right, look for what's different. Ooh, oxygen double bond to carbon. Remember when I say what's different, what's not carbon, what's not hydrogen, what's not a carbon-carbon single bond. Ooh, a nitrogen. And it's got two R groups on it. I'll call R prime and R double prime. The carbonyl carbon here has carbons, I'll call R. So this is R, and these two I'll call R prime and R double prime. And this is an amide. And how do we make an amide? A carboxylic acid plus an amine. And if we come back here, what's R? 3 carbons. And I'll have my carboxylic acid group. What's my R prime and R double prime on nitrogen? Well, they're the same, so I can use this shorthand. This is one way of writing it. And I'm done. And that's how you make amides. Now, once you have an amide, what can you do with it? I think I was just starting to talk about this last week, and I don't know how far we got into it, but I thought we'd back up a step or so. And now let's talk about acid hydrolysis. I think I mentioned this or got into it, but a little review never hurts. Now that you have a carboxylic acid, amide, if you react it with acid and water, what happens? You break it down, you get back the carboxylic acid you would have used to make that amide, and the amine salt of the amine used to make that amide. Now, it turns out this reaction is very important, and we're going to be coming back to it later on. Why is it so important? Well, how many of you, I think I mentioned, but I'll mention again, how many of you have heard of the word proteins? I think you all know what proteins are. And they're made up of amino acids, which we're going to get into later on. And how many of you have heard of a peptide bond? Give me a thumbs up. The rest of you too can help out. All right, and thank you. And what's a peptide bond? Well, I'll teach you later in the semester. It's really an amide bond. And where can you find acid and water? In your stomach. It always amazes me, one of the great miracles of life, that we all have cells in our body that synthesize hydrochloric acid, which is why our stomach's acidic, because it helps break down the food. And one way is by acid hydrolysis of an amide. And I'll go more into that when we get into later in the semester, proteins and amino acids and peptides, which we will get to. Now, it's important to know that you get the amine salt. And why? Because if I have HCl and water, you'll get back the carboxylic acid plus the amine you would have used to make that amide. However, in the presence of acid, this happens immediately. Remember, amines are bases, proton acceptor, and HCl is an acid. So this is an acid-base reaction, and there's nothing quicker than that in all of nature. And sometimes I'll write it this way. You see me enough times when I have things above and below the arrow there with no numbers. That means react this with the stuff over and below the arrow. And this is acid hydrolysis of an amide. This is an amide. Carbonyl with nitrogen to that carbonyl. And if you have an amide, whoops. Remember, R prime and R double prime can either one or both be hydrogen. And if you add acid and water, what you'll get back is the carboxylic acid you would have used to make that amide and the amine salt of the amine. You would have used to make that amide. So if we look here, I'll call that R. I have a methyl group on nitrogen, I'll call that R prime. And then here, this hydrogen on that nitrogen, I'll call R double prime. And therefore, if we look at what we get, I'll get acetic acid, and then R prime is methyl, R double prime is hydrogen, and you add two more hydrogens to make the amine salt. You could have also written this like this. Either one is correct on the test. And that's how you do it. Let me remind you that if you don't put the amine salt but put the amine down there, I'll mark it wrong. Because in the presence of acid, this is the fastest reaction in all of chemistry, acid-base reaction. So let me share the fun. And your turn. Why don't you try what would be, and on a test, I would have done this so you know there are two products. What would be the organic product or product of the following? And when you're done, give me a thumbs up. Everybody all done? Can everybody still give me a thumbs up if you're done? All right, I think everybody's done. Let's do this. What do we have that's different? Oh, wait, I see a question. That's fine, Tom. And then if you want, Tom, the nice thing about having a video is you can stop it and take all the time you need, which is one of the nice things why I do the video. All right, thank you for your concern. All right, what do we have that's different? Carbonyl. Carbon double oxygen, that carbonyl is nitrogen. We have an amide. And remember, R prime and R double prime can be hydrogen. In this case, they're not. And what happens when you react an amide with acid, HCl, and water? You get the carboxylic acid you would have used to make that amide, plus the amine salt of the amine you would have used to make that amide. And as I mentioned earlier, if you don't want to show charges here, you don't have to. So what's our two carbons? What's R prime? It doesn't matter. I call this R prime and this R double prime, or reverse, it doesn't matter. So what's my carboxylic acid? Here's my R group, carbonyl, OH. What's my amine salt? Sorry, this is 3 carbons right here. And here's my chloride anion. And that's how you do it. And let's try the following. What would be the starting material that you would react with HCl and water to make these two compounds? 3 points each. And don't forget, give me a thumbs up. Anybody who would like to put up their answer, please feel free to. Anybody who'd like to turn on their webcam, feel free to. Remember, when I see faces, it makes Dr. White more energetic. And trust me, I can always use all the energy I can get. All right, I think everybody's done. Let's do this. In order to determine what would you start with to react with HCl and water, you look at the products. What's different? Carbonyl hydroxygroup carbon, carboxylic acid. Ooh, two R groups on a nitrogen with two hydrogens and a chloride anion. That's an amine salt. And what do you react with HCl and water and amide? And remember, R prime and R double prime can be hydrogen. In this case, they're not. So I can call this R, and these are the same. I can call R prime and R double prime. So our amide, R group, carbonyl, nitrogen. What's my R prime? R double prime? CH2, CH3. Now, that's one way you could write it. And you could also write it this way. And either one would be correct on the test. And that's how you do acid hydrolysis of an amide. And like I said, we'll be coming back to that again, because that's how your body, mine and yours, break down protein to make amino acids. In other words, that's how you digested that steak you had yesterday, or the hot dog, hamburger, or if you're a vegetarian, I guess the right term now is vegan, if you had soybeans or other plant products that have protein in it, that's how your body breaks it down. Now, this is acid hydrolysis of an amide. You can also have base hydrolysis of an amide. And the base I'll use for this class, I'll just stick to for this reaction, sodium hydroxide. If you take an amide, react with sodium hydroxide and water, you get not the carboxylic acid, but the carboxylate anion of the carboxylic acid you would have used to make that amide, plus the amine you would have used to make that amide. Let me explain why you get this. And remember, R prime and R double prime can be hydrogen. I could use other bases, but I'm going to stick to this. Now, when you first hydrolyze this with base and water, what you actually get is the carboxylic acid plus the amine you would have used to make that amide. But this can't be isolated. Why? Because this is a base. And a carboxylic acid is an acid. And you learned when we did carboxylic acids, if I react this with a base and water, I'll pull off the acidic proton to make the carboxylate anion. And remember, the fastest reaction in all of nature and all of chemistry is an acid-base reaction. So as soon as any of this is formed, it will immediately, faster than I can say the word immediately, like in a billionth of a second, a nanosecond, it reacts and forms the carboxylate anion. And if we look at the problem on the whiteboard, time for awful humor time. Didn't know they named a board after me. Whiteboard, never mind. I said awful humor time. I warned you. And if we look at this, what's different? Carbonyl with a nitrogen. This is an amide. And when you react that with base and water, sodium hydroxide is a base. You get back the carboxylate anion of the carboxylic acid you would have used to make that amide, plus the amine you would have used to make that amide, and our prime and our double prime can be hydrogen. In this case, they're not. So if we look here, I'm going to call that R because it's attached to the carbonyl carbon. What's on the nitrogen? One of these I'll call R prime, the other R double prime. And now our group is 2 carbons. And I'll get the carboxylate anion of this carboxylic acid. And then what's our methyl, nitrogen, benzene ring? And those are 2 products you get. And I see a question, so I better go check it out. And the answer is Justine, of course. I did warn you I had the quickest mouse wheel finger this side of the Mississippi or the other. And when you're done, let me know. Ah, you're done. Good. One thing I didn't do with this problem, on a test, since there's going to be 2 products, I put a plus there to let you know there are 2 things you got to do. So have fun. And when you're done, don't forget, give me a thumbs up. Thank you, Cynthia. Thank you, Anna. Oh, I'm learning everybody's name. No, I can see it on the screen. All right, anybody need more time? Well, in that case, I'm gonna get moving. All right, question is, what's the organic product or products? Remember, these are the building blocks organic chemists use to make things, and Mother Nature uses to make things too. So if I look at this, what's different? Ooh, carbonyl, oxygen, got my attention. Remember, whatever's not carbon, what's not hydrogen, or what's not a carbon-carbon single bond should get your attention. Ooh, nitrogen there too. And this is an amide. And remember, our prime and our double prime can be hydrogen. And in our case, one of them is. And when you react an amide with base, sodium hydroxide, and water, what do you get? You get not the carboxylic acid you would have used to make that amide. You get the carboxylate anion of that carboxylic acid because you're in base. And you also get back the amine you would have used to make that amide. And if we look here, that's R. One of these I call R prime, the other R double prime. So my carboxylic acid would be benzoic acid. And then my amine, one of the R groups is methyl, the other is hydrogen, and I'll add one more because amines have 3 bonds to nitrogen. And you could have also written it this way. And that's how you do it. Oh, let's do one more. These are fun. And the question would be, what are the, and on a test, I'd help you out, what are the 2 products you get when you react that compound with sodium hydroxide and water? Anybody who'd like to put their answer up to their web camera, let me know, and I'll unpin myself so you can have the full screen with your answer. And when you're done, give me a thumbs up. I see one already. Oh, I got to try this once more. Well, I think everybody's done, except for one person. I'll hold off. Give you another 15 seconds. Hurry up. No, take your time. All right, let's do this. What do we have that's different? Ooh, oxygen, nitrogen. We have a carbonyl, carbon double bond to oxygen, nitrogen. On the nitrogen, we've got carbons, I'll call R prime and R double prime. And on the carbonyl carbon, we have an R group. And remember, this is an amide. In this case, it's not true, but just to remind you, R prime and R double prime can be hydrogen. And when we react it with sodium hydroxide, a base, and water, you get back the carboxylate anion of the carboxylic acid you would have used to make that amide, plus the amine you would have used to make that amide. If we look here, R is methyl. One of these I call R prime, the other R double prime. Therefore, I get the carboxylate anion of the carboxylic acid you would have used to make this amide. And my amine, one R group is ethyl, the other one is a benzene ring. Doesn't matter which side you put these on. I could have swapped them, and I have a hydrogen because there's 3 bonds to nitrogen. And that's how you do that. All right, I have everybody's attention. I have a very important announcement to make. As of now, I have gone over all the reactions, general reactions that I will teach you this semester. You can all go. The rest of the semester, we'll be taking those reactions out in the real world. And then the fun starts. We're going to have a good time. But no more general reactions after the one I just did, amide with base and water. I will do later in the semester a modification of one of the reactions, but I don't really call that new. Another one I'll teach you in the lab and also in a class I won't put on the test. So good news. We've covered all the general reactions you have to know this semester. Yay for you. Now, Dr. White knows about another 350 more general reactions, but this is only one semester course, and I had to zero in on what I felt was the important ones for you. But I thought you'd like to know that. What would you react with sodium hydroxide and water to make those 2 compounds? That looks better. Anybody want to hold up their hands to their webcam? Anybody not want to hold up their answers to the webcam? Anybody just want to turn your webcam on? Or you have a bad hair day? I've been having a bad hair day now for a couple of years. It's called It's Going Away. I shouldn't complain. My best friend, who I've known since sophomore year of high school, that's over 50 years now. By the time he was in his late 20s. He lost most of his hair except for a horseshoe. Oh, do we kid him? And when I started losing it, he started kidding me, and I say, look, I still got more than you. All right. Anybody need more time? Give me a thumbs up if you need more time. Anybody want to hold up their answer to their screen to show the class? I guess not. All right, let's take a look at this. We have two products. What's different? Carbonyl with a minus oxygen. This is a carboxylate anion. Ooh, nitrogen with two R groups on it. This is an amine. Remember, R prime and R double prime can be hydrogen. In this case, they're not. So I'm going to call this R prime and R double prime, two methyls. These four carbons I'll call R, and therefore, what do you react with sodium hydroxide and water to get a carboxylate anion and an amine? And the answer is an amide. And now, if we go back and look, R is 4 carbons. And N and R prime and double prime are methyls. And that's how you do it. And if I look at the clock, guess what time it is? Time for Dr. White to get up and do his little stretching. And with that, I'll see you in 5 minutes at 1:55. Do come back. right, let me get everybody back. Got to change the batteries on this. That's better. Welcome back. Oh no, everybody shut off their webcam on me. Oh, there's someone. Thank you, Martin. Some of the other people, if you could, turn on your webcam. Makes Dr. White feel better. All right, before I get started, I just realized I forgot to ask. I hope you all had a nice, happy Passover. For those of you who celebrate Passover like me, unfortunately, too many matzah balls and matzah. Passover is not a low-calorie holiday. Trust me, it's not. Now I'm going to spend the next couple of weeks losing the weight I gained during Passover. And for those of you who celebrate Easter, I hope you had a happy Easter and you got all the chocolate eggs and chocolate rabbits you wanted, or whatever else you'd like. And for those of you who celebrate neither, I hope you had a nice weekend. All right. Now, like I said, with the last reaction, I have covered all the general reactions we'll be doing this semester. But the rest of the semester, I'll be taking those general reactions and show you how they apply in our everyday life. And now it gets exciting because now you think of it like you've learned a vocabulary. Now you get to read stories like fiction and other stuff. Well, in chemistry, organic chemistry, now that you've learned the general reactions, now we can see where they are in our everyday life. Now, we're talking about amines, and I'm going to be next couple of slides, shutting off. Will this be on the test? But I want to talk about some things that are important that you should be aware of. Now, some of those things I would like to say up front. I am in no way making a moralistic statement for or against it. It's just organic chemistry. And unfortunately, from my point of view, it's the dark side of organic chemistry. But first, can everybody see it? Switch is totally off. Now, there's a whole area of chemistry, I wish I had more time and I talk about it, but I don't, called diazonium compounds or aromatic diazonium compounds. Now, a diazo, not a diazonium, a diazo is when you have two nitrogens with a plus charge. You usually have a benzene ring on there, and you've got an anion of a chloride. And this is called a diazo group. And you make those from nitro groups, which is why putting a nitro group on a benzene is an important thing to know how to do. Now, once you have again, I'm going through this quickly because we're not going to, you have a diazonium or azo compound, you can react it with an aromatic ring. Usually it's phenolic with a hydroxy group phenol. And this is called a diazonium azo coupling. And these are diazonium compounds or azo compounds. Now, it turns out these type of compounds are dyes. How many of you can see my red shirt? Or whatever color you're wearing something. As long as it's not white, how did it get that color? Well, they use an artificial dye. And what does a dye do? It absorbs all the colors of the rainbow, white light, except the one you're seeing. So all the light comes here, is absorbed, the dye absorbs it, except red in this case. Or if I had a blue one, it would absorb everything but blue. Well, what does that? Those azo dyes, about the late, I might be off by about 10, 20 years, 1800s, organic chemists found that they could make artificial dyes. It could be even earlier. And that was quite lucrative because before that, most people wore white, which is not. I am, but anyways, I said I was getting into awful humor Monday. Oh, it is. But they found a way to make artificial dyes, and boom, everything took off. And now if you look around society, we're all nice and colorful in the clothes we wear, if you want to be that way. Now, turns out other molecules that you can get from nature can be used as dyes. Because everybody sees this real complex and switches off. And this is called the indigo dye. It comes from the indigo plant. And what color is it? Blue. And when you put this on cloth, it becomes a very deep blue. And what do we call that very deep blue? Royal blue. Why did it get the name royal blue? Because in the Middle Ages or earlier, who had money to take and dye their clothes a dark blue, almost a purple? Only the king and nobility. The peasants or the shopkeepers didn't have that kind of money. And that's how it got its name, royal blue. And that comes from a plant. But it's a lot cheaper now to use synthetic dyes, which we can make in a chemical plant. All right, switch is still off. I'd like to talk about alkaloids. And alkaloids are nitrogen-containing compounds that are obtained, and the word extracted means you obtain it from plants or plant material. And alkaloids have major, major physiological effects on your body. And you'll see. Now, I didn't take let me see if I can find a better example. This is morphine. Morphine is a painkiller. It was used in World War II extensively on the battlefield.
I think I'm an example of that, the morphine.
I don't think they use that. I'll get to something else they might use on you, and I might not get to it, but this is a nicer image. Now, if we look at this is a complex ring system, which I haven't talked about. Well, let's look at some things you do know. Oh, a benzene ring with a hydroxyl group. That's phenolic. Oh, oxygen, carbon here. That's an ether. Another carbon with a hydroxyl group. These wedges and dots tell stereochemistry. Is it above or below the ring, which I haven't really taught this semester. We'll get into a little stereochemistry in carbohydrates. The dark wedge means it's above the plane of the ring. The dashes means it's below. Oh, look, you know a double bond. And if we look over here, I have a tertiary amine. Carbon here, every bend in the line is a carbon, and a methyl group. So this is a tertiary amine. Now this is morphine. It's a I don't know if it's still even used these days, painkiller. Now, how does it kill pain? I have no idea. I'm an organic chemist. That's a whole other field that I know nothing about. And not that I wouldn't want to know about it, but I've centered my studies and knowledge in what I do. Now, if you modify morphine, and everybody see, let's see, which one is it? Yep. See the hydroxyl group up here on the benzene ring? It's an alcohol. If I'm taking alcohol and react it with a carboxylic acid, what do I have? I have an ester. and the rest is unreacted. And if you do that, this is the same structure, just drawn a little. All I've done, oh wait, actually this is different. If I take an alcohol and react it with the alkoxide from an alcohol with an alkyl chloride, I make an ether. And this is coating. And coating is a quite good painkiller. Are you ready for a Dr. White story? Of course you are. Back when I was about 10 or so, I came down with asthmatic bronchitis, which was not fun at all. That whole summer, I just stayed in the house because I was coughing my lungs out half the time. Good news, I survived, in case you were wondering. But the other good news is my father was a pharmacist with his own drugstore. And he brought back to me a big bottle, a quart bottle of elixir terpene hydrate with coating. And it's the best cough medicine ever made. What is it? It's coating, the molecule, and 80 proof alcohol. So if it doesn't work, you don't care anyways. And it worked. It worked. Trust me. Sometimes in a coughing fit, if I take a couple of tablespoons of that, I stop coughing. I also feel good too. Well, I got better, but I was still taking that couple of tablespoons, like a shot or two, but it was tablespoons before I went to school. And my father one morning at breakfast said, "You don't need that. You're better now." And I said to him, "But I do. It makes me feel better." He said, "I bet it does." And he took the bottle back to the pharmacy because think about it. I was having a buzz every morning before I got to school with alcohol coating. But coating is a very important painkiller. Now, if we look at morphine or coating, and if we take those two hydroxyl groups and react them with acetic acid, do not try this at home, and there are other better ways to do it, you make this compound. And this compound is called heroin. And it's a very addictive illegal street drug, which they make. And for a while, until they stopped selling it without you signing it or prescription, illegal drug dealers were taking codeine and converting it into heroin, which I'm not going to tell you how, but anyways, and that's heroin. Now, another alkaloid, something that's a nitrogen compound that comes from a plant and again switches off, is this one, and it's cocaine. I think you've all seen in the movies, Dr. White doesn't do drugs like that. I do aspirin when I need it, but actually I don't even do aspirin anymore. I use ibuprofen, but for many years now, this has been a street drug, cocaine. And if you look at it, you have a nitrogen carbons here and here, methyl group here, end of a line. You have an ester here, an ester here, and this is a molecule that has enormous effects on people's physiological state. How? I have no idea, but now you're starting to see this. Now, this is a complex ring system. This is called a bicyclic system. This is a 1, 2, 1, 2, 3 bicyclo compound. And Dr. White worked with in graduate school. My research wasn't with amines. This is called bicyclo 2,2,2-octanone. And the molecules I was working with was this diketone, which I made in my research. But this is a complex bicyclic ring here, and there's one right up here. And this is cocaine. Now, nitrogen compounds are found, and this is a very important compound, important, and has caused a lot of problems in our society, called methamphetamine. It's a small molecule, got a nitrogen here, methyl here, carbons, the secondary amine, got a benzene ring, and this is a very addictive compound. When about less than a year after it hit the streets and it was becoming a social problem, people were dying from overdosing, other problems. There's a magazine put out by a weekly, it used to be weekly, now it's monthly, by the American Chemical Society called C&E News. That's short for Chemical and Engineering News. Everybody calls it C&E News. And the article in C&E News is so heavily checked that it's always very factual. And they had I can still remember this many, many years ago, a major article on methamphetamine, also known as crystal meth, because it's a white solid. That's how it got its nickname, crystal meth, and how addictive it was. And I was shocked by when I read that people who take it just once are addicted, just like that. Thank goodness I don't. I hope none of you have problems with it, but it's addictive. And it can be easily, here's ecstasy, which is similar to methamphetamine. You have the same, this area right here is this area, the benzene ring. The only difference here is you have the acetal of formaldehyde attached to this ring. And how that does what it does in rave clubs, I've never been to a rave club, but from what I've seen on the news years ago, this was quite popular there, keeping people up and also high. And you can make it from this compound, which is made from the derivative of the sassafras tree. And our government's keeping eyes on people who buy that because they know what they're going to do with it and they usually get arrested. But all these drugs who are painkillers or used for other things are nitrogen compounds. Now, switch is still off, but just in case you're wondering, what are certain amides? Well, silk is an amide. Wool is an amide. My skin, your skin, what's left of my hair, your hair is an amide. And because it's made up of proteins, and proteins are natural occurring amides. Now, protein chemists have sort of masked that by using the term peptide and peptide bond. But if you're a synthetic organic chemist like me, hogwash, that's just an amide. Important one. Now, I'll talk later when we get into polymers about nylon, so I'm going to skip this. All right, part of this, I just turned the switch on. Now I'll show you which part. Let's talk about heterocyclic compounds. And it turns out heterocyclic compounds are the largest class of organic compounds in nature. This you should know. What is a heterocyclic compound? It's a compound containing carbon atoms and other atoms in a ring. Hetero meaning different. And those other atoms you should know are oxygen and nitrogen. Again, you should know what is a heterocyclic compound. It's a compound containing carbon atoms and other atoms in a ring, and those other atoms are either oxygen or nitrogen. I can't think of one where you have both in a ring. Now, many of them are aromatic. As you learned, I had to switch off. If you have 2n+2 pi electrons in a ring, that's aromatic. But you should know that a heterocyclic compound is a compound containing carbon and atoms in a ring, and the other atoms are oxygen and nitrogen. I'll take a drink of water while everybody writes that down. Hint, hint, wink, wink, say no more. All right, switch is on. I'm only going to ask you to learn one heterocyclic compound, and that's pyridine. And pyridine looks like benzene, except you remove one of the carbons and replace it with nitrogen. And this is like a tertiary amine. Well, it is. And pyridine is aromatic. Pyridine is both the IUPAC and common name. So on a test, if I asked you draw the structure of pyridine, I would hope you know that. Now, pyridine does not undergo electrophilic substitution easily. That means putting things on the ring, but this does react like a tertiary amine and does undergo nucleophilic substitution. Now, one thing I should tell you, I've worked with pyridine. Imagine this. Take a dead fish or two, put them in a Ziploc baggie in the middle of summer, put them in your backyard in the sun, and come back 2 weeks later and smell it. Pyridine smells about that way, if not worse. It's stinky. It's probably the stinkiest non-sulfur containing or thiol compound that I know of, but it's very useful. Now, I think I did, but someone remind me if I didn't, and please use your speaker. Did I talk about my mouthwash and how it saved my gums with a quaternary ammonium salt? Oi, hold on. Bad doctor, wait, I'll be right back. Blame it on. Whoa. I'm back. All right. Unfortunately, in my family, dental problems run hereditarily quite severe. And many years ago, I was having gum problems, and I was going to an outstanding dentist. I wish he was still alive. But anyways, and he put me on this mouthwash that cleared up those problems. Well, one problem was prescription, and a small bottle, like less than a pint, was $70 a bottle. Insurance didn't cover it. Second of all, it turned your teeth light brown unless you kept on brushing it real hard, which was not fun either, but it saved my gums. Well, unfortunately, that dentist had to retire because of health problems. It was sad, but true. And I went to another one. I was in between dentists because I didn't like the new one. And my gums started hurting me. And I was running out of this mouthwash. I said, wait a second, I'm an organic chemist. I read the label and said, oh, I know what does it. So I went to the local Walmart and I went in there. I went to where they had the mouthwashes. And there's two types. One is the Listerine type, because I looked at the label, and that's got a phenol compound that does the antimicrobial. So I bought some. I bought the Walmart. It's cheaper. Walmart brands are identical to the name brand. They do a good job in terms of quality on that stuff. Their generics are pretty good for a lot of things that I've bought. And guess what? my gums were starting to hurt. So I said, all right, I'll go back. And the other type of mouthwash is a Scope, which they have their house brand. And if you look on here, you'll see the label. And I bought this. And I said, oh, that uses a quaternary ammonium salt. And on here it says cetyl pyridinium chloride. And that's a trade name for a quaternary ammonium salt. And all of a sudden, no pain, because when I was having pain, if I did this, I'd be in a lot of pain. And I've been using it ever since. By the way, Scope this size costs about $6, $2.25. So it's cheaper to get theirs, and it's identical. And how does that do that? I think I told you quaternary ammonium salts have good antimicrobial properties, and that's that. Now, what's pyridinium? Chloride. Let's take a look. Here's pyridine. The molecule in that mouthwash and acetyl group is C12, if I remember correctly. CH2, 12 carbons. And how do you make that? Take pyridine, react it with an alkyl halide, C12, in a base. Remember, tertiary amine attacks that, forms a quaternary ammonium salt. And this is something you learned, except not with a heterocyclic, but this is like a tertiary amine. And think about it. I keep on telling you, the things I'm teaching you are in your daily life. What can be more daily life than my mouthwash? I wonder if I can get some kickback on product placement in my course. Nah. Anyways, that's an important use, and pyridine is used in other things too. And it kills all the bacteria on my gums and keeps me nice and healthy. And plus, it's not $70 a bottle, and it lasts more than 1 month. All right. Switches off. Mother Nature does amazing things. Everybody see folic acid on your screen? You see it? Thank you. And if you follow the news over the last many years, folic acid is an important compound for our diet that keeps our body healthy. It's especially important for small children and pregnant women, but also the rest of us. How it got its name, I have no idea. How Mother Nature made this, but up here, carboxylic acid. Oh, another one. I have an amide here, benzene ring, secondary amine, and a very complex heterocyclic compound. Now, how does that help us be healthy? I have no idea. And do I expect you to know the structure of this? No, I don't. I know where to look it up. But I also know that this comes from spinach, which explains why Popeye was so strong, and other green leafy vegetables. All right. I'm going to be going through a few more stuff. Click. I'm turning the switch. Will this be on test to the totally off position? But I thought you'd like to learn about some other heterocyclic compounds. Now, a 5-membered ring is called parole. How it got that name, I don't know, but that's the name. And this is aromatic, 2, 4, 6 pi electrons. 2 of the pi electrons are non-bonding electrons. And this is pyrrole. Now, it turns out pyrrole rings play an important part in our life. You say that about everything, but let's look. If I hold on, somebody has a question. Thank you, Thomas, about helping with iron deficiency anemia. I wonder if it can chelate with iron, I don't know, or bring it into your body. But anyways, porphyrins, again, switches off, are macrocyclic compounds. Macro means huge. I mean, huge, gigantic cyclic rings that are made up of pyrrole rings. You look here, here's one pyrrole ring, here's another, here's a third, here's a fourth. And this has got a name, and we call that type of ring a porphyrin. Now, you can find porphyrins in two important type of compounds. One is heme, you know, hemoglobin, and the other is chlorophyll. Now, in hemoglobin, the heme, you have an iron in the center here associated with the nitrogens. And then you have various proteins attached to this. That's hemoglobin. And hemoglobin, the heme part, helps transport oxygen to our body, cells in our body, and removes carbon dioxide. How? I don't know. I sort of vaguely. Now, when instead of iron, you have a magnesium +2 cation, that's chlorophyll. And that plants use to do photosynthesis. And part of that helps because of the aromatic system ring. This whole thing is aromatic. And these are pyrrole rings here that connect together, make up the heme or the chlorophyll-based ring system. Now, another heterocycle, again, switches off, is an indole. The indoles are this, and it plays an important part of key amino acids like tryptophan and serotonin, which is good for your brain, I think. Now I'm getting well beyond my knowledge of the human body. I did that 2 days ago or longer. And again, I'm just sort of, you can come back. Now, this is a very complex, and you saw this, I believe, in folic acid. This is called a purine. How it got that name, I don't know. But it's a key building block in caffeine and theobromine, which is a major ingredient of cocoa, which is chocolate. And it's also used in DNA and RNA. Now, switches off. Here I have caffeine. Notice you have the heterocyclic ring on this nitrogen, this nitrogen, this nitrogen. You have methyl groups. And if you've ever been addicted to caffeine, and I was when I was younger, when you withdraw from that, you go through withdrawal symptoms. You can get addicted to that like anything else. And at one time in my life, I used to drink a lot of Dr. Pepper and Coke. Then I switched to tea, and tea, actually, the black teas I drank had more caffeine than the Dr. Pepper or Coke. And when I cut back, I started feeling uncomfortable for a while, went to the doctor and explained what was going on to me. And I've cut back to now, instead of doing like 8 or 10 mugs of tea, I only do 2 a day, and sometimes only 1. And it doesn't bother me when I cut back. Now, this is caffeine. And right here, this is theobromine. The only difference between caffeine and theobromide, this is rotated 180 degrees, this nitrogen right here has a hydrogen in theobromine, cocoa, on this in caffeine, that hydrogen is a methyl group. How many of you ever heard of someone who's a chocoholic, who's addicted to chocolate? I'm not, thank goodness. I'm addicted to other things, but not that. And it's amazing that where most people can get addicted to caffeine, some people, you make the slight change, replace the methyl group with a hydrogen, and this also is addictive for some people. How it is, I don't know. And we're done with the nitrogen. That went quick. All right, remember this Wednesday, we'll go through the carboxylic acids and esters. And I've got to look at the syllabus, but I think a week from this Wednesday is test number 3. We're sort of caught up. Hold on, let me take a quick look. Test 3 is scheduled for 4/14. Yep, I was right. Sorry about that. What that means is I have covered everything that's going to be on test number 3. This Wednesday, we'll do the practice problems for carboxylic acid and esters. Next Monday, we'll do the practice problems. I'll go through it for amines, quaternary ammonium salts, and amides. I'll also do my world famous review for next test. And we're back on track. Because remember, I postponed 2 of the tests, which I think did well for you. But as normal, even if we were face-to-face, I'm picking up the pace a little because you've all lost your rookie status as organic chemistry knowing students. So we're moving along, but there's still plenty of time because I always try and finish more than a week ahead before a test. So what does that mean? We're going to go into new material that will not be on test number 3, but will be on test 4. And that happens during the semester. It happens even worse during the summer. By the way, if you know anybody who needs to take organic chemistry, Chem 170, I'm teaching it this summer. Let them know to sign up. It will be totally online. So if they don't live in the area, they can still attend because it's online on the internet. All right. Now, next chapter I'm going to go through is polymers, synthetic polymers. Just so you know, with my background and working in that area, I could give a 2-semester graduate level course in synthetic polymers just on that alone. So I'm going to teach you everything you wanted to know about synthetic polymers in an hour or so or less, which means we're just going to go through some basic key things that'll help you understand it, but it's nowhere an in-depth covering because I only got 16 weeks, and I'd rather spend more of that on carbohydrates, fats and oils, and proteins, which are things more likely you're going to use in both your daily life and your professional life. All right, everybody see synthetic polymers, chapter 14? Thank you. All right, switch is on. What is a polymer? You should know a polymer is a macromolecule built by repetitive linking of smaller units called monomers. Now, if you look at the word polymer, poly means many, mer means unit. Over here, monomer means one unit. So a polymer is where you link many units, repetitive units, to make a macromolecule. Now, what do I mean by macro? First of all, let you all write this down. Switch is on. I'll never ask you what poly means or mono means, but a polymer, meaning many units, poly, many, mer, units, are made by linking repetitive units of monomers. Now, one way to think of a polymer, how many of you have ever been stuck at a railroad crossing with a long freight train? I mean, long. The boxcars or the tank wagons all together. Well, if you thought of each one of those boxcars as a certain repetitive unit, like if they're all the same brown with the name on the side, that's what a polymer is. There's units repeating, just like a railroad boxcars linked together. By the way, I just did knuckle coupler. My hobby, one of them is model railroading. When I was about yay little, my father did something amazing that got me hooked on trains. He took me to one Sunday morning to the south side of Chicago to the train repair area for that hub, all the trains. And I was young enough that they still had steam engines. We spent the whole morning watching them take steam engines, putting them on the turntable, moving them and moving other cars. And we went back there a number of other times. I loved it. Ever since, I've been a train enthusiast. Even though Amtrak I can leave, but European trains are awesome. All right. So polymer, and when we talk about units, we're talking about macromolecules that may have up to 1 million carbons in it. I don't know about you, that's huge. Now, switch is on. When we talk about polymers, there's two types of ways of classifying polymers. One is by their chemistry, and one is by their physical properties. When we talk about their chemistry, there are two types you should know. One is an addition polymer, and the other is a condensation polymer. Again, based on chemistry, of all polymers, you can break them down into two groups: addition polymers and condensation polymers. Come to think of it, all the work I've done in polymers have been addition polymers. Nope. One of these years I'll remember to put in the following slides. Now, an addition polymer, the way you can tell that has only one type of monomer. Think of a train, long freight train, and every boxcar is identical. And you got hundreds of them, millions of them. That's an addition polymer. So you should know that an addition polymer has made up of only one type of monomer. There are millions of them, or at least a million, but it's all the same. Just like if you had a train with all the identical boxcars, printing everything, what's inside, it's all identical. Now, you should know examples of a addition polymer. Now, one is saran wrap. Or the clear plastic wrap in the kitchen. I know it by the trade name. I think many of you did. That's an addition polymer. Another one is anything rubber. And I'll just use an example, a rubber car tire. I don't know if they're non-rubber car tires. And those rubber, this is made up of an addition of the same monomer to make rubber. Now, saran wrap, and this you don't have to know, is called polyethylene. And it's this repeating unit, CH2, CH2. And N is on the order of greater than 500,000, usually up to a million, 1.5 million, if I could spell it. So this repeating unit keeps on going and going and going for long, long periods, and that's saran wrap. Now rubber, is this molecule, polyisobutylene, and its monomer hang on, I wrote it wrong. Sorry about that. Usually I don't make mistakes, but as you've learned throughout the semester, this diene, di double bond, is the monomer that makes this one. And here in rubber, N is the order of about 500,000 to 1 million. That's an addition. You should know. Addition polymer. That's a polymer, one type of monomer. You should know what are examples of addition polymers, saran wrap or rubber, like in a rubber car tire. And with that, if I look at the clock, it's just about time for us to take our break. So I'm going to say, let's take our break, come back in 5 minutes at, I'm about a minute early, but don't tell anybody and give me about an extra 30 seconds. Shh. But anyways, come back at, oh, it just changed on the clock, 2:50, and we'll continue with polymers. I'll see you in 5. I'll be right back. I forgot to get a refill on my water bottle, which is running low. I'm back. Let's get going. All right, we're talking about polymers. Example, the water bottle is a polymer. I'll talk more about that. And polymers play an important part in our daily life, just about everywhere. My lenses, my glasses are polymers too. All right, we're talking about polymers, speaking about, that's better. But anyways, we're talking about polymers, and one type is an addition polymer. And you should know an addition polymer only has one type of monomer. And examples would be saran wrap or polyethylene is the actual name. That's the clear plastic kitchen wrap. I use it, and I'm sure you do. And also rubber and car tires. You should be aware that's an addition polymer. Now, the other type of way of indicating by chemistry types of polymer is a condensation. Let me make sure I've. All right, everybody see that on the screen? Thank you. Thumbs up, people. And a condensation polymer is made up of two different or more, but I'll just do two different types of monomers. And examples of this would be polyester, such as my water bottle, or pop bottles. Remember, Dr. White's from the Chicagoland area. The stuff in bottles that's carbonated, non-alcoholic, we call pop. If you haven't had Verner's, you're missing a lot of good things. Also, nylon, such as a nylon jacket, is a condensation polymer. That's where, think of a train where you have not only box cars, but you have tank cars. Or some of the box cars are blue, some are brown, and some might be yellow. You can have more than two different, but the main types are two different ones. And these are condensation polymers. So next time you see a water bottle and you're with a bunch of friends, you can say, do you know that's a condensation polymer made up of two different types of monomers? And another one that I'll talk about that's a condensation polymer are urethane. And Dr. White just has a handful of patents in urethane polymers, so I might know a little about it. Example, urethane insulation. If I can spell, which I can't. All right, what did I just do here? All right, I just lost. I see what I did. Sorry about that. Let's see if I can pick up. Somehow I clicked on the outline view, which I've never done with my tablet. I never will again. I think I'm spelling insulation right. I was always first one down. And also not only insulation, but cushions. If you like sitting in a car or on furniture and it's not like rock hard, like a piece of metal or piece of wood, you're sitting on a urethane cushion, like a pillow, and that's made for polymerization, and it's a condensation polymer. All right, now there are two types of ways of identifying polymers. One is by its chemistry, and that's the addition polymers and condensation polymers. The other is by a physical property, a key physical property. And one type is the thermoplastic. This one I do have a slide. I guess the dreaded eat one of your slides virus got this file. But anyways, a thermoplastic, and by the way, switch is full on. A thermoplastic is a polymer once formed can be reheated to form a new shape. Example would be once you make the polymer, you can make it like a water bottle. And I can heat it up again, the plastic, and reshape it into a different type of bottle or something else. And another one would be saran wrap, polyethylene. I can melt it, heat it up, and form into other shapes. Now, one of the interesting things is there's no correlation between condensation and addition polymers and the properties I'm talking about. There's just not. You got to know them. All right, so a thermoplastic polymer is one once formed can be reheated to form a new shape. Another way of saying you can recycle it. Now, the other type is a thermoset. Once it's formed into the shape it's going to be, you can't reheat it, cannot reheat it to form a new shape. An example of that is rubber, like in rubber car tires. Phenolic resins, which I'll talk about, and urethanes. You can't reheat it and reshape it. Once you made it, you're stuck with it. And how many of you have ever seen, well, I'll let you copy this down. So if I ask on a test, what's a thermoplastic polymer? You should know it's a polymer once formed can be reheated to form a new shape. If I ask on a test, give an example of a thermoplastic polymer, we could put down nylon jacket, polyester would be a water bottle. If I ask on a test, what's the thermoset polymer? And that's one, a polymer once formed cannot be reheated to form a new shape. What would be an example of thermoset? Rubber tires. Now, how many of you have ever seen in the last 10, 15 years, unfortunately, even now, in the last year, it's been in the news, where you see civil unrest in a certain area, and you see the protesters putting car tires across the road and setting them on fire. And you see flames come out. Why? Because car tires are thermal set polymers, and all it does is melt a little and burn. It just doesn't melt into a goop at the bottom, it actually burns. And one of the worst type of fires, I've heard a couple of them over the last couple of decades, is there are places in the United States and elsewhere in the world where, since you can't recycle easily car tires, they've got millions of car tires in these dumps. And once one of those catches fire, it takes years to control that because this keeps on burning. It just doesn't melt down because it's a thermal set polymer rubber. Now, just a quick thing. I'm going to be turning the switch off. I could spend a whole 4 weeks on addition polymers. Now, they're formed by what's called free radical polymerization. What's that? Now, it turns out you can have a molecule where on a carbon has this one electron, has no charge, but this is called a radical. And since it's alone, it's called a free radical. And these are very energetic particles or molecules or intermediates that want to react with anything. And what do they like to react with? A double bond. And this attacks that. The one electron goes there, and it forms a new radical. This switches off for this slide. And this can react with more of the monomer. Notice I have a radical here. And this can react with more of my monomer to keep on building the chain, where this is a repeating unit, Z on CH, CH2, where N can be 500,000 to million. That's huge. And this is how saran wrap is made, and rubber is made the same way. Oh, hold on. I don't know why my computer doesn't do it 112. Hang in there while I shut this down. Sorry about that. All right, and I have a slide for this. Here you have a radical initiator, that's the R dot. And oh, they use L, not Z. I got them mixed up. And you form this polymer, where N is huge, 500,000 or longer, million, and that's big. Now, the switch is totally off. I just thought I'd show you a few things. When L is a hydrogen, polyethylene, you know that as saran wrap. Now, this has the common name ethylene, put a lot of together, we call it polyethylene. When L is a methyl group, we call that propylene. That's the common name, not propene. And we call it polypropylene. How many of you ever bought electronics or a flash drive or something and it's got that bubble shell on top, the plastic, and you try and get through that? It's almost impossible. You get your sharpest things to try and open it up, and you go, oh, I hate this. Well, that's polyethylene plastic. That's that polymer. It's very strong, which is why they use that to protect things like if you bought a flash drive on a card or other things that come on a bubble on a card. Now, when L is a benzene ring, we call that, this monomer is called styrene. It's a common name that became the IUPAC name. And you make a polymer of that, we call that polystyrene. How many of you ever seen the white cups insulated for hot beverages or cold beverages, or the super cheap coolers that are made of that white, very lightweight material? Not the better coolers, but the cheaper ones. That's polystyrene. That molecule come together. Now you're learning about all these molecules. Like I said, I'm taking it out in the real world where we have some fun. And some of the others are, and one thing I do want to talk about is vinyl chloride. That's when L is a chlorine. And when you put them a lot together, we call that polyvinyl chloride, and we call it short PVC. And if you look in your bathroom or other places in your house, you know the white pipes for your plumbing, plastic, that's PVC, polyvinyl chloride. And that's a addition polymer where it's the same monomer linked over and over again. All right, switch is on. Now, if you go back to about 1800, when they in certain Pacific islands found rubber trees and found the sap of that was this, I'm going to use a very scientific term, goop, that you could get the water out of. And you got this sort of, sort of interesting stuff that was hard to make into stuff. And that was rubber. Well, wait a second, I just go out, I can look outside my door or go out in the shopping parking lot, a lot of a shopping part up there, a shopping store, a supermarket in their parking lot, and I can see car tires, and they're made of rubber. And that's not a goopy stuff. What happened? Well, it turns out, think of polymers as long pieces of string. And if you have a bunch of long pieces of string, you pull it this way, it's got a lot of strength. But if you go like this, the individual strings fall right apart. Well, that's the problem with things like rubber, natural rubber at one point. And like I said, by the way, switch is full on now. And think of each one of these as a long polymer molecule. And if I pull it this way, it's got strength. If I pull it this way, it comes right apart. So that's not good. Well, it turns out in the early 1800s, people were looking at how do I make things, natural polymers and other things, stronger? And turned out one person, I'll tell you a semi-sad story, came up with a solution. There are a number of people who are working on it, but he was the first one to patent it. And that's called cross-linking. And cross-linking, the switches on, are links, chemical bonds between polymer chains. And by linking them together, you make them more rigid and it affects the other physical properties. You make it stronger. And this is called cross-linking. Let's take a look at this. If these lines are polymer chains, if I chemically bond them together like this, every once in a while have chemical bonds here. This is a chemical bond. I still have my strength going this way. Now, if I pull it this way, it's not going to fall apart. And this is called cross-linking. And who was the first one to come up with cross-linking in a commercial way or patent it? Somebody called Goodyear. Anybody ever hear that name, Goodyear? Why am I thinking rubber tires? Goodyear tires. And Goodyear, about 1820-ish, give or take 20 years, came up with the practical solution how to cross-link rubber so you could mold it and make things made out of rubber, which today we obviously know car tires is an important thing. Now, what you don't know is a couple sad things. One, the original Goodyear, I can't think of his first name right now, was an alcoholic. And two businessmen realized the potential of his patent, which he did patent, his invention, and came to him and said, we'll give you a large sum of money if you sell us the rights to your patent for cross-linking rubber, making rubber, and allow us to use your name. And he did. And then he went and proceeded and drank it all away. Sad part of life. That happens with alcoholics, unfortunately. Excuse me. And there was never a Goodyear ever working in Goodyear tires. They bought his name and his fame and his invention. Now, how did he do that? He found with rubber, if you added sulfur, called vulcanization, that would react with the double bonds to cross-link it. How many of you have ever smelled rubber burning? Like if you leave a rubber, peel out from a stoplight, if you have a big engine in your car, or just fan belt rubbing and start, it stinks, right? That's not the rubber, that actual rubber. It's the sulfur that's in the rubber, the cross-link that's burning, and that makes it stink. And that's called vulcanization. How they got that name, I don't know, because I don't think anybody's here from the planet Vulcan. I'm a Star Trekkie, if you haven't guessed that. Yes, I am a science fiction person. But anyways, that's cross-linking, and you should be aware of cross-linking. We're doing the book. I'm skipping these sections. Anybody reading the book? Now, let's go back and talk about condensation polymers. And they're made with two different types of monomers. Each monomer has two or more functional groups. Switch is off right now. And usual functional groups that you make condensation are esters and amides, which you know how to make an ester. Now, there's another one called a urethane and another really good one which I've worked in heavily, both the urethanes, that's reacting phenol with formaldehyde to make what's called a phenolic resin. And then epoxy resins are another one, which I haven't shown you the chemistry. Well, I showed you a little of it. Switches off. If we take a diacid, di meaning two carboxylic acids, and a diol, OL and ending alcohol, di, two alcohols, you can make a polyester. Now, this is just the first step, but a polyester would have this repeating unit where N is the order of 500,000 to a million. And notice the key linkage here is this ester. And it's formed right here. One of the hydroxyl groups, one of the carboxylic acids. Again, switches off, and polyesters play an important role in our daily life. Here's one right here. I didn't have to go far to find one of those. Now, polyamides are also important. And polyamides are made by reacting with a polycarboxylic acid, dicarboxylic acid, and a diamine. With a poly being a diamine. Now here's an example I have here. If you take this amine, diamine, mean there, two, diamine. Now this is called an acid chloride. We talked about it earlier for another reaction, but acid chlorides are like carboxylic acids, but much, much more reactive. So amine plus a carboxylic acid derivative will form an amide. And you generate HCl, hydrochloric acid, which is why you have a base here. And you form, in this case, this polyamide. And if you make fibers from this and weave them together, we use them in bulletproof vests. This is the structure of Kevlar. And I'm sure you all have heard of bulletproof vests the police wear to protect them. Thank God they have those, or a lot more would be unfortunately severely injured or killed. And that's that polyamide, layers of it that are very strong. What makes it strong? The aromatic benzene ring doesn't want to flex. And those pi bonds holding hands in a circle make it real strong and give it its strength so it can be made into a material that's layered on sheets and makes a lighter weight bulletproof vest. Now, the military also uses ceramic plates for what they call body armor, but that's inorganic stuff. No. Now, switches off. Polyurethane polymers are made from what's called the urethane reaction. And a urethane switches off for this, uses a polyisocyanate with a polyol. Poly meaning many, isocyanate. This is an isocyanate function, and it reacts like a super reactive carboxylic acid. And when you have two of these in the same molecule, you can form polymers. And the general reaction, by the way, there's a mistake on this slide. Oh my gosh, one of these days I'll correct it. This is like an alcohol reacting with a carboxylic acid, and this is like an ester. But when you have a carbonyl with oxygen, R group, nitrogen to the same carbonyl, R group, this is called a urethane. And I've done a lot of work in urethane. In fact, hold on one second. Time for Dr. White's show and tell. Now, when you're working in the urethanes like I was, and when I was first started doing that, I wasn't a section, I was still a bench chemist. So I was making my own urethane foams, and I developed a new molecule, group of molecules that help make a better type of urethane foam. And to test that, I had to make a lot of urethane foams and test physical properties. Now, the badge of courage of a good urethane foam formulator if they can make something special. And that something special is you take a cup where you made the urethane foam, you pour it out, and you have enough catalyst in there that as soon as it hits the ground, it stops and solidifies. This is solid urethane foam. And here's my badge. I've had this for a long time. And it took me about 5 tries, which is pretty quick, to get it where it solidified and held the cup up like that. It's dust collector too. And I don't know how many hundreds of urethane foams I made to test my product to get for the patents I had, a lot of them. But after I'd been starting working, someone told me about, have you done this yet? And I said, no. They explained it. And like I said, took me 5 tries, but is that wicked? That's my badge of honor in urethane foams. If you're good, you know how to make one of these. Now I got to put it back in a safe place. Hold on. Anyways, that's urethane. And urethane, you mix a polyol, and polyol means many hydroxyl groups. And one of the more useful polyols comes from sugar that's reacted with ethylene oxide. And I'll teach you a little more about that later on. But that's the urethane. Now, another reaction to make a type of polymer is called a phenol formaldehyde polymer. And the reaction you use is sort of like an aldol condensation. Now, phenol has an acidic proton, switches off, and this is the phenoxide anion. If you react it with formaldehyde, this reacts here because this goes like that. And what it gives you after rearrangement is this called the methanol. And this can react with other of these to form a polymer. And that's called a phenolic polymer or resin. Resin is a fancy name for glue. Everybody see this? This is called a pre-polymer. We can stop it at this point. The CH2s react with OCH2OH, react with each other. This has got a mistake. There should be a couple where it has CH2OH on the end here. They don't, and that's a mistake they've made. And this usually has a molecular weight about 700. And then you can stop it here from polymerizing any further. And then later on, when you add a catalyst, you can make it polymerize so it solidifies, gets a very high molecular weight, and this is a good glue. And also other types of phenolic resins. This is called a resol, which is liquid at room temperature. And there's Novalax, which are solid.